of force the components are getting, which connection is getting more stiffer, which connection is getting more weaker. So these types of uh, output result we can get. So first of all, start from the scratch. I have just only imported this model. This is a very normal design. All the components are in the form of circular and rectangular shapes. So make it more innovative. So in the motion analysis, first of all, I need to ground my body, ground my component. Which component would be the ground, so that if I run the simulation, my component would not fall due to the gravity. So I just this bar would be the ground, this bar would be ground, and after that I just want to create the joints. So once I click on the joints, so it will automatically find the joints and apply joints accordingly. Which joint would be the rigid or which joint would be the, you can say, the active or revolving joint or sliding joint, automatically it identify. Once I click, now it's all done. And I just want to optimize this part. So I need to software, I need to tell to the software that this part, this part only will be optimized, not the others. So for doing so, we just make it a design space. Once I assign this component as a design space, now all the work will be done on this component only. So I just want to give a motion. I just want to give a motion. Let's see. Provide the motion to this disk by motor. I just put a motor on it. Now these are the you can say the various input parameters are available. You will be able to get the freedom to put the motor input. If you know about the angles, then put the angles. If you know about the speed, then you can also put the speed. If you know about the acceleration, know about the torque. So these types of input interpretation you can do with the use of the motor. Plus and minus, you can put the make it into the anti-clockwise or clockwise direction. So motion has been given by this motor. And one more thing I have to do. I don't know why it is not hiding. One more thing. Go to structures and set the symmetry planes. So basically these shape controls are deciding parameters. You can say the deciding parameter for any optimize or any concept design to make that component as a manufacturable. Suppose if I am not giving the shape control to my this bracket, then software will optimize it by it, but it will optimize this particular bracket by itself only. There will be no any symmetry between the axis, and the optimized design would be very difficult to manufacturable. there are lot many improper ribs, you can say the very thin ribs you can get. So it is very important parameter, that is the shape control. It will decide your manufacturability. So suppose go to the shape control. Now it is asking me to select the, you want to make it manufacturable by a single draw, split draw, extrusion, overhang. What type of manufacturing constraint you want to give to your component during the optimization or during the concept design. So I just make it to split draw. Now it is asking me to select the, in which axis you want the this manufacturing constraints, in x-axis, in y-axis, in z-axis, in which axis I make it in x-axis. Same, just like the I just want to make it symmetry. Okay, so my component would be symmetry in the z direction as well as in the x direction. So if my component would be the symmetry, then it would be very easy to manufacturable, because before going to the product manufacturing, we have to fabricate its die. Then if there would be no any symmetry available in the component, then it would be very difficult to fabricate the die or to design the die. So I would put the symmetry planes. I want symmetry in up and down as well, right and left as well, in x axis. With respect to x axis I want symmetry, with respect to z axis I want symmetry. So that's it, you are done with the model setup. Now it's time to run the analysis. So once you run the analysis, then it will show you some you can say the, first it will simulate your motion analysis. In the motion analysis, it will extract the loadings, how many types of loading are this component is getting during the motion, and what would be your peak load, and what would means to say the maximum load, and the what would be your the minimum load. And according to your loadings, then it will try to optimize your component, scoop out the waste material from the this bracket. So before going to simulation, I just open another window, because if I put it on the simulation, then it will take around some 5 to 6 minutes to get completely simulated. So I have already simulated this part. Just to showcase you, I just open that results. Where it is, this is the parasolid file, and this is my results. Go to open.
संदीप झालं ते बोलणं माझं.
Participants are requested to mute themselves.
सर ते लाईट नसल्यामुळे राहिले जरा मारायला.
So yeah, I have imported the file, this file having the results. So first of all, the same setup is there, the same setup is there, but there are no results, but this file has the results, as you can see. It is showing the optimized bracket. So first let's see the motion. What's the motion it has? So make it animation. So this would be my motion. This motion depends on my motor inputs that we have given during the model setup, and this bar has been set as rigid, so that is why it is not falling down due to the gravity. And due to this motion, all this mechanism is running. So but you can see it is running, but you are not able to get the loads, how much type of loads you are getting on component, on connections, on anything in the model. So you can also get the plots, and you can also get the behaviors. Suppose, what is the name of this component? Just this is the flywheel and the balls or bracket. So go to parts. Uh, rigid part 2. If you click on the displacement, then it will show you the displacement graphs. If you click on the angular displacement, these are the angular displacement plots. Basically, it is showing the, you can say the, showing the plots of the movable parts. Anything you can check. Check the velocity in x direction, y direction, z direction, and total magnitude. If you want to check it only in the z direction, then you can click on those parameters. Okay, and you can also get the loads. Just make it side, click on the concepts. Now here you can also get the uh, what type of forces this bracket, you can say, or you can say this whole assembly is experiencing during this motion, what type of torques you are getting, what type of reaction forces you are getting from this particular mechanism, and these loads would be carry forward for the topology optimization. I just show you one more thing. Here we have calculated all the forces. We have calculated all the forces. Now it's time to carry forward this forces for the optimization. So you can directly go for the optimization, optimize the part. So which part you have to optimize, because you have already selected as a design part. So software will, analytical tool will work on this design space on this. So once you open the optimize the part, then there are some lot many more options are available to optimize part. Topology optimization means to say, if you want to play with the remove the materials, you can say. Topography optimization, if you want to make these strengthen your make this strengthen your sheet metal parts. If you want to get the suggestion from the software from where you want to get, where you want to make the ribs, and where you want to make the gussets to make the sheet metal component more strengthened, more stiffer. So topography optimization will work on that. Gauge optimization will play on the thickness of your material. Suppose if you have 10 of thickness, but if you don't want to optimize that, you want only the what would be my optimum thickness of my plate or sheet, so you can play with those things. So topography and gauge optimization are the go for only the, you can say only go for the mm, sheet metal type of parts. And lattice parts, and the lattice part, these structures are come to in picture in the very latest time. You can also, you I think, you can also check the latest design on the latest drones, the company which are making right now. So I just give you some picture of the latest design. So in that manner, it try to optimize your part. This one is the latest design structure. So maximum material has been removed. Only ribs are available to strengthen the part, or you can say to make the part more stiffener. So basically, these types of lattice design structure are not manufacturable by the traditional manufacturing processes. Basically, these lattice design mostly manufacturable with the 3D printer, or you can say the polymer 3D printers. So next, it would ask you to select the mass target. Which mass target you are targeting? Basically, you want to play with only 30% mass of your total weight of component. You want to play with the 25, or you want to play with the 20. Sorry, 20% mass of your component. So I just click on the 30% total mass of this bracket, and here you can also check the objective. You are means to say you are mm, optimizing this particular part to get what. So basically, if you want to optimize your part to get the more stiffness, then select the more stiffness. And to get the maximized frequency, then click on the maximized frequency. Then it will work on your only the resonant frequency and natural frequencies. And to minimize the mass, then you can also select the for minimize the mass. Basically, its objective is to lightweight the component. So I will work only stiffness only, because I want my component lightweight as well as more stiffness. So once you click on the run, then it will show you the results like this, just like this. So according to the loads that it was experiencing during the multi-body dynamics, and according to those loads, those maximum loads, those minimum loads, then software also suggests you this type of shape. So you can also make it using the casting simulation. You can also make it using the extrusion as well, and you can also fabricate the dies for these types of brackets. And I have one more example, but it was not so perfect. Yeah. So first, in the first iteration, I I got this type of bracket shape, but in second iteration, I got this type of shape, because uh, loading is the same, but there is some difference between the, you can say that there is difference between the symmetric plane, difference between the manufacturing constraints. So according to that, it changes the shape. So this one is the first iteration, and this one is the you can say the second iterations. So I have optimized this part. Okay, so with my experience, and you can also with your experience, you can also say that this component is castable. We can make it from the casting process. So I have optimized the component, as well as we can also check its manufacturability in the same platform. Go to the manufacture. So we can work with the topology optimization. We can work with the sheet metal type of parts. So if you are working on the topology optimization, then you can also check the porosities. Then if you are working on the sheet metal part, then you can also check the thinning percentage and FLDs, forming limit diagram, just to predict the material behavior, how the material will behave during the forming simulation, forming process. So I have run its manufacturing simulation. I just show you. Then it will not the whole process simulation, but it will suggest you the where you can get the porosity location, porosity shrinkage location. Basically, I have taken all the parts, whole part I have taken, so that is why it is showing some shrinkage porosity in the middle bracket. In the middle bracket, if I talk about the upper bracket that we have optimized, so you can also get the porosity locations in the manufacturing. And my concept has been generated. Concept is clear. Now I am happy with this optimized design. So this design you can also make it. You can also take out from this platform to your CAD platform to make it smooth. Because why it is so rough? Because all these are the mesh that those mesh has been editing. Those mesh has been edited during the simulation. So some extra elements that you got during the simulation that has been removed, so that is why it is showing some rough surfaces. And these rough surfaces you can also remove from the polyneuts, or you can also take it out from this platform to your CAD platform to make it smooth. So once you make it smooth, then you can also further take it for some process simulation or the process analysis. Suppose if you want to check its casting process or castability, then you can separately go for the casting simulations. So basically this tool is especially used for the concept generation. You can full-fledged generate your concept. Just check the feasibility of your component. Is it manufacturable or not? If it is manufacturable, then check its whole process simulation, whole process analysis using some separate analytical tools. And from there, you can able to get some more idea about the design changes or the die design changes. So from where you have to make the changes in your design and in your component. Then after that, run the again detail level simulation, just to freeze the design for the manufacturing. So we just close this tool. My, you can say the, my concept design is freeze. Now I will check my detail level analysis. Start from the casting. Software is opening. So once it opens, then I will show you the whole process for model setup to result outputs. So this is the general user interface of the casting process simulation tool. All the commands are similar to our previous tool in which we develop the concept. Some geometric commands are same, but in casting panel, these are some specific casting commands are available. Casting ribbons are available. So without wasting the time, I just directly import a model. Gravity. Okay. So I have just imported a model. So let me check there are results associated with it or not. Yeah, results are there. So for doing the casting simulation in the ALTAIR, analytical tool, only 5 commands would be required. So suppose this is the different part, optimized part was the different. So suppose you got the part, finalized part, and if you want to check the castability or manufacturability, and if you you also want to predict the defects at the very earliest stages. So first of all, assign the component, just to tell the software what is your finished component. And during the assigning, then it will ask you to select the materials and its grades and its initial temperature. Initial temperature means temperature of the molten metal during the injection. So let's make it into the mm. So what would be the molten metal temperature during the injection? And if you want to check the material library, or you can say the create your own user defined material, then you can also do. So material library is opening. Yeah, so these are all the material groups. aluminium, brass, steel, cast iron, cobalt, and nickel, gold, silver, tin. So as per your application and as per your requirement, you can select the materials and grade as well. If you want to check the grades in EN standard, in ISO standard, in ASTM standard, and JIS standard, so you sorry, you can select the standard as well. So basically these are the fluid property of this material, these are some thermal properties of the material, and these are the phase change properties of material. Phase change means because we have to simulate the biphasic simulation in which filling and solidification will be done simultaneously. And if you want to make it your own material, or you can say the customize these materials, so you can easily edit these parameters. You can also edit these parameters. So I have just assigned it to the steel. Okay, now it's time to assign the gravity direction, in which direction gravity is applying force, applying gravity is there. So for this part, I will make the gravity in Z axis. Yeah, it is fine. By default, it is fine. And next process is to assign the gate. So at which location you want to enter your, uh, you can say the molten material into the cavity, into the die. So so I want to inject my material from this location. So here you can also move your move your getting location as per your convenience, up and down, and also you can also rotate these locations, and you can also change the cross section area. If you want to take it into the square or rectangular shape, then you can also select. If you want to make it into the only circular, then there's that thing also possible. Right click and exit from the command. My getting location decided, and my component decided. Now it's time to assign the component. So basically, in the first run, I just want to run this component only, without any component, without any casting component, just like the core, just like the chiller, riser, sleeve, overflow. So I will not apply these things. I will not apply these things. I just want to simulate this component only, just to check how the material is behaving in this cavity. And to understand those material flow, we would apply these components in next iteration. Okay, and after that, these are the processes. So which process you want to, for which process you want to analyze this component. Suppose if you want to go for the basic setup, in the basic setup, uh, either you can also put the initial velocity, if you know about the initial velocity of the material, or filling time. Then if you want to go for the casting process, in the casting process you know about the filling time, then you can also put. If you know about the spoon height, at what height spoon is pouring the material into the component, then you can put. If you know about the flow rate, then you can also put the value of flow rate. Any one of the four, if you know, then you can make those parameters as the input and put the value of that. And in the gravity process, you can also put the, you can also go for the tilt pouring and investment casting as well. So initially I will select the spoon height with 50 mm is sufficient to pour the material into the cavity and run analysis. So you observe one thing that uh, we don't need to do the meshing. We don't need to do the geometry cleanup. We don't need to make the contacts between the two bodies. Basically, we have done the contact in the previous analytical tool, but in this casting process, we have just clicked the geometry and it automatically create the gate, automatically create the gravity, automatically suggest you to select the component to apply the material and pouring temperature of this particular for this particular component. So once you click on the analyze tool, then it will ask you to select the element size. That's it. If you know about the element size, then means to say it will also suggest you this would be the perfect element size for this type of component. Then if you want to make the fine mesh, then you can also edit the value, or you can also leave it as default. And these are the analysis type. Analysis type means to say which analysis you want to run. You want to run only filling analysis, in which it will show you the filling behavior of the molten material, or you want to simulate only solidification analysis, then it will, in this particular analysis, um, it will show you the result during the metal solidification region or metal solidification phase. So I want both filling and solidification simultaneously. So I have already results associated with this. So I just directly click on this. So where is my animation bar? Here. So here you can see, I just play the animation. So it is showing you the molten metal behavior in this cavity. And here you can also get the temperature contours. So make the simulation in a loop. But during the filling stage, it would be very difficult to identify the defects. So just to predict the defects, we will check some another output results as well. So just make it stop and go to another result type. So just to defect prediction, we check the solid fraction. Solid fraction is the result parameter in which you can able to get those location in the component, on that component, on that material is getting freeze during the filling stage. Molten metal is getting into the cavity, but during that stage, at some region in the component, your steel or your aluminum is getting solidified. So I just play the animation. So you can observe these locations, this location, this behind rib location, and this side bolt location. Metal is still filling, but this region is trying to get solidified. So there is a lot many more temperature difference between this location and this location. Temperature is drastically fall down, due to which the material on this location try to get solidified. So this type of output result help us to predict the lamination defect. So in which the component in the component region, there are two or three, you can say, the find the layer in the component, and that doesn't look good in the aesthetics of the component. It will destroy the looks of the component if your component is very useful in the aesthetic, just like the some bathroom, you can say the bathroom type of component, faucet, shower. So in this type of casting, these aesthetics will play a role, very important. And next is the velocity. Basically, in the velocity, it will also help to identify the gate velocity. If your gate velocity is very high, then there would be uh, more chances to mold wear off or die wear off in very short period of time. So here you can also check the gate velocity and the velocity directions. I can use the call out also, just to check the contour at various locations. And after that, the most important parameter, that is the last air cause to your component is the blowholes or the bubbles available in the castings. So red region showing uh, air is entrapping with my molten metal. So once the air got trapped into your component, then it will also affect your mechanical properties of the component or mechanical strength of your component. So these would be some region on where air got trapped. After that, these are the pressure values, how much pressure is being exerted by the molten metal during the filling, and these would be my filling time. You can also manually check after the 1 second how much component, how much cavity filled, after the 2 second how much cavity filled, and in 4 second how much cavity is filled. And this last red region showing metal is not filled in this location because air also uh, means to say air also occupied its space in this location. These are the cold shirts. Basically, cold shirts are the localized weld when two front flows meet together at some particular region. But if there is some very high temperature difference between the two front flows and they try to merge together, then it will make a weld line type of thing, you can say, or the can be cold shuts. But in this region, cold shuts are not available. So I just show you the airflow pattern, how the air is escaping from the cavity when the material gets in. So basically, transparent part is your molten material and blue color part is your air. So this is the air displacement. In the last is it rotate. get success to get some space to occupy the space in the component in the last region. So this is my feasibility check test, in which how can we check my feasibility of my component only. Suppose if you are not getting the result from this particular gate point, then you can also modify this gate point. You can feed this component from its below, you can feed this component from its top, and you can feed this component from its back. So just to get the results and move towards the solidification. In this solidification, you can also get the of the call outs. You can also get this solid fraction. So basically, what is the meaning of the solid fraction? Solid fraction means to say the regions which are getting solidified in the last. So in the casting, there is a thumb rule. The region which is that is solidifying in very last, then there would be some tendency to have the shrinkage porosity. What are the last location? So these are the last locations. So what's the reason for these last location? Because if you see the component, there is a more thicker on this location. So it is showing you the solidification pattern, how your component is getting solidified, in how much second, how much component, how much region of the component, how much portion of your component solidified. And just directly correlate this solidification pattern to the shrinkage porosity. Now select the porosity. Now it is showing the porosity location same as the you can say the same as the solidification pattern, because 1 2 3 1 2 3 4 for these four reasons were the these four reasons were only the last you can say the last solidification region in the solidification pattern. Let's check once again, just go frame by frame. Yeah, these four locations, 1 2 3 4, these four locations are shown as the porosity. And if you talk about the microporosity, basically microporosity, then you can go for that. There is a little more microporosity here are available in these regions. If you want to check the porosity, means to say the just a minute. Porosity volume, then go to the shrinkage volume. You can also get the uh, total size of the void. Then you can able to get how much void would be created due to this shrinkage. So it is showing the volume basically. So with respect to volume, you can idealize the size of this void. And this analysis is all about a component level only. Suppose if you have already design a component, then how can you simulate those? So for those, again import one model. Yeah. So in this, I have attach one runner, attach these two risers, basically these two risers and this runner. Those things are not were created into the CAD software. These creation will be done with the help of only the geometry panels and some casting components. So all the processes are same. So I just delete the risers and I will create the component. Suppose I want to create a riser, then go to the riser, then select the region. I will select the region, it will create the riser. Now I just need to put the dimension of these. Suppose if you want to put a core, then click on the core. Once you click on the core, it will automatically highlights the region on that core can fit. Suppose I want to make a core on this red region, just direct click on this. It will automatically create the core. Then it will ask me to select the core material. What would be the material of my core? It would be the furan sand, it would be the green sand, silica sand, steel. So select it as a silica sand. What would be initial temperature? Or 20 degrees 20 degrees Celsius temperature is sufficient. If I make it simplify this code, then you can check this. So all the processes are same. I have put the material input region on this runner. Then now I just show you the results. Now material is filling just like this, and due to having the riser, extra material come to the risers, and I will show you the defects. Then you can compare the previous results and this recent results. Then you will able to find that there are less defects are associated with this particular model. So let's move toward the first air entrapment, because in the last iteration we got the air into the model in the top region, but by using the riser, these air shift from this location to the riser location. And risers, up once the casting get done, solidify, then we will break the riser, because risers have no use with the finished good. And these are the some remaining location for the air entrapment. Then we can make it remove by using the uniform cooling, or making the mold temperature continuous, or more consistent. Then these air entrapment can be removed. And in solidification, we were getting some shrinkage porosity on this particular region. Now let's check the shrinkage porosity. So there is a very little shrinkage porosity is having, but there are not very big holes are there. Because if I show you the solidification pattern of this particular component, now you will able to see the last solidification region. Yeah, the last solidification region has been shifted to the riser. These regions are solidify at the earlier stage, but gate runner and the risers are still in liquid phase, liquid stage. So, your shrinkage porosity also shifted, also moved. And let's check what is the amount of just this little pore. Where I think that was due to the shrinkage porosity, because it is a very small in the dimension. That is why it is not appearing in the dimension region. It would be very small. So this was about the casting. So I just give you some glimpse about the sheet metal forming simulation and injection molding. So if you have any doubt and question regarding the concept design and how we can make the manufacturable those concept designs and validate. If you have any question, then you are free to ask.
All the participants can unmute themselves, and if they have any question related to the knowledge shared by Sharad sir, they are free to ask. All the participants, if there is any question. Thank you, Sharad sir,
So I
for
think
the
there is
very
no question.
informative
So
knowledge shared.
let's.
And right now, I don't think any participant is having a question. Uh, we can continue.
Yeah, no problem. No,
Okay.
we can move forward. So
Yes.
I just close this tool and apply another tool for the sheet metal forming analysis. How can we validate our sheet metal component designs? So all the tools from the Inspire family have the some look-alike type of GUI. All the geometry panels are same, but this relates from the sheet metal forming simulation. So it has some two menu bar are also there. First is the feasibility and second one is the tryout. In the feasibility region, I have explained you earlier in my previous session that feasibility, in the feasibility we just open the blank shape and get the fit analysis and the nesting analysis just to predict the how much sheet or how much material we are utilizing or how much material we are wasting from the complete coil or a particular shape of sheet. And in the tryout process, we just simulate our blank or sheet metal with respect to the die, punch, blank holder, draw pads, and constraint pins. So all these types of things. So first of all, I just import a model. I accept one model from my history itself. So so no problem. I think this is a solved model. So open the geometry. Just give me 2 seconds. This is the parasolid file, and I just import this parasolid file. So first of all, I have import this particular component. So we just design this component, and with the help of the optimization, we just able to reduce its part, and software also suggests us these three ribs. We just need to provide just to increase the strength of this part. So now it's time to check its proper feasibility. Proper feasibility and its process analysis. How the sheet metal will behave in the production stage when we do the production or when we do the physical experiment for this particular component. So first of all, this is a thick component. We just make it a mid surface of this. Mid surface has been extracted. Right click and exit. Now this is the surface only, and like some other tools, it has also some you can say the video tutorial associated with it, just to use the command properly. Right click and exit. So basically, to use these simulation driven design platform, there is no as setup, means to say, you can say the as setup procedure you have to follow for set up the process and running the simulation. Basically these commands are set as per the process. Just follow first command, follow second command, follow third command, and move accordingly. So next command is just to defeature. Defeature means to say, if you want to fill the holes and cutouts. So I just want to fill the hole and also remove the cutouts. These are cutouts. So I just want to fill these cutouts. Cutout filled, and I also want to remove this flange removed, but I want a hole this, yeah, because I have to apply a constraint pin. So with respect to this hole, this blank will be open. Next is the material. So click on the material, inbuilt material library will open. So these material library are set as per the European, English and Japanese material standards. There are a lot of materials are available from low UTS to very high UTS. And in this tool as well, you can also make your customized material. There is also a available option, or you can also edit your existing material. So you can also edit some existing FLC, failure limit curves. So randomly I just picking a material DDQ, deep drawing quality material. Right click, apply the thickness. I just take the default thickness, click on DDQ, material assigned. Now it's time to move towards the next command, that is the orient setup. Orient setup, basically, what is the meaning of the orient setup? So orient setup, just to, you can say, the in which direction component has been stamped. So once I click on the orient setup, now it is showing me the automatic orient setup location, but in the actual manner it is very difficult to place the component just like this in this inclined shape on the machine. So just try to make it in a very simpler way. When I click on the X direction, now it is showing me some red and yellow color, because what is the indication is that it is showing red color means it has negative draft up to 10 degree to from 10 degree to 68 degree, because you can able to form the component in X direction, but it will not come out from the die, because there is uh, very high value of negative draft we are getting. So select in Y. Once I click on the Y, there is no negative draft we have found. Just right click and exit. Next operation is to apply the constraint. Constraint means to say if you have already applied the blank holding force or already applied the draw pins, constraint pins, then you can apply those things. I just want to create the blank holder, select the surface for the blank holding force. I want to make a blank holder on this outer region. A blank holder has been created. So according to the shape and size of the component, software also suggests you to the three values for the blank holder: low, medium, and the high. If you agree with these three values, then you can go for that. If you want to add it, then suppose I just want to take the value of the blank holding force up to 10 ton. So 10 ton force, it will automatically convert into a Newton. And I want to constrain my blank from this location. Just select the edge of this hole. My blank has been constrained. Now it's ready to run the analysis. So I just directly show you the analysis. So these are the results for that particular setup. Here you can also see during the feasibility test, you can also get the thinning percentage up to 45% on this particular region. And you can check the thickness values. You can check the thickness value as the various location using this call out. Just click on the randomly on the component, then you will able to get the thickness values on the various region. Okay, next is the FLD. That shows you that your component is in the good condition or in a very bad condition. So it is showing fracture, means to say it is showing a red color mean the failure, and the on the failure line we are getting some points, so it is getting fracture over here. Close and go go to the thinning, and if I run the animation, now this is your open blank shape. Open blank shape means to say now you have got the open blank shape. Now it is very easy to get the material utilization. So how much material will be utilized from your coil? So for those things we need to open my blank. and you can also get the press tonnage of those. The maximum press tonnage would be
कैसे हैं
required
बॉस?
of this
भला प्रभु जी बहुत
this value. Now you have opened the blank. You have opened the blank. Now it's time to do the nesting analysis. So nesting analysis means we have created the blank. Now I just want to make this blank utilization, how much material is being utilized from my sheet. So sheet or coil. So here I have selected as the coil, and here I have also put the value of my material cost and my scrap cost. So once I go for the run the simulation, then it will show me the results just like this. So it is showing material utilization. Maximum material utilization is the 84.61%. Let's see how my open blank shape is oriented on the coil. Just click on the report. Now you can check the nesting report. What is the part to part margin? What is to part to edge margin? How your component is fit into particular coil shape, and what is the material utilization. 84%, that is a very good material utilization. And here you can also get the uh, material cost per blank and scrap cost per blank. Means to say you are utilizing material up to 85% and wasting only 15%. So that is a very good yield you are getting. So for opening the blank, you will able to get these types of data uh, before jump to the fabrication or before jump to the die designing. So quickly, I just show you the process simulation. How you can simulate the whole process using the uh, die punch and binders. Just go to the tryout. Let me extract one file. Import one geometry. So I have imported a geometry in which I have only one blank available and one die surface available. So we will try to extract some other die component from this die part only. So in the tryout, you have to move according to the you can say the according to the sequence. First of all, I need to assign my blank. Once I assign my blank, then it will ask me to select the thickness and the material. I just go for the default values. Now next, add operation. Suppose if you want to do the crash simulation, then crash forming, then go for the crash. If you want to go for the single action, then go for the single action. Double action, lancing, trimming, spring back. So I will go for the single action. With the automatic tool configuration, I just built my some remaining tool bodies. So automatically punch has been created, blank holder has been created, and my die surface was also there. So that is ready to go. Now setup is completed. Once you click on run the analysis, your simulation will put on run by the software. and after running the analysis you will able to get the results just like this. Just like this. I just show you the animation. Here you can also check the meshing, because this is not the meshless technology, but the software does the mesh in its background. So you can also review the mesh once the analysis get completed. So just isolate the blank. You can also check the behavior of your blank during the simulation. Just make it slow. Loop, play. If you want to the whole process, check the die binder punch, then you can check and make it stop, isolate the blank, and you can check its manufacturability by using the output results. Thinning is sufficient. Now check the formability, FLD, just to predict my component is fracturing or not. My component is not fracturing. My component is running fine. And what would be the you can say the stresses your component is getting during the forming simulation or your die is getting? So all those things you can predict. So these are the value of the uh, stresses that the sheet metal is experiencing during the simulation, during the not the simulation, during this forming process. And you can also check the transitions in mesh. This is the transition in mesh. Earlier all the mesh are very big in size, and once the forming gets started, all the mesh uh, start break down into the small pieces. So with the help of this process, you can validate or you can improve your design, sheet metal component design, basically not the all design but sheet metal component design. And you can make the more efficient sheet metal components, and you can also freeze the design of your component. And once you freeze your design of your component, automatically you will go for the die designing for those for that freeze component. So you can also validate the component as well as die before the fabricating. So basically this was all about the sheet metal forming simulation. So if you have any doubts, so you can ask. Then I will move my last segment, that is the injection molding analysis, in which you can improve your design, improve your plastic design, and some if it required the modification, if it required the modification in the component, the die, then you can also uh, predict at the early stages.
Participants are free to ask any questions. All the participants can ask any query. I think, Sharad sir, we can move further.
Yeah, sure. So this is our last segment. Just to I will just explain you and just take you a tour to set up for the injection molding part validation, or how we can improve our die design, product design for the plastic components, basically, especially process we adopt for the injection molding. So quickly, I just import a model. Which model I should take? Okay. Suppose this one is the full complete shot. Full complete shot means to say this is the handles you have designed in any CAD software, and along with these handles you have created the gates, sprue, uh, cooling channels, and you want to validate both the things simultaneously. You want to analyze both the things simultaneously. You want to uh, check the defects in the component and check the process. Basically, this whole design, usually people do the simulate this whole design for the die validation. If they design a die and do this type of complete short simulation, then with the help of this short simulation they will able to get the both type of result. They can able to get the defects in the component, and they can able to get the material flow pattern, how they can improve by modifying their dies. So first of all, select the component. Select the component means to say which plastic material they have and plastic grades they have, and after that importing molten metal temperature. So I have taken the only, means to say only default values. Just right click and exit. After that I just go by the automatic process. Once I click on this component, oh, not go by the automatic. Automatic it is not taking. So do it manually. Component assigned. Now let's move toward the next command, that is the runner system. Runner system means to say in which we need to define the feeding system. What are my runners and what are my gates? So suppose it is asking for me select the gates. So I have already made the gate. So I just quickly assign those. Suppose if you have not already made gate with your CAD, then you can also make your gate here only. So same for the runner. These are my runner. This is my sprue, and this would be my injection point. This would be my injection point. At from this region, my molten plastic will try to inject in this particular shot, and after that, now talk about the runner specification. Suppose if you want to configuration for the hot runner mode or cold runner mode. So basically, if you automatically assign all those things, so basically it will by default go for the cold runner mode. Suppose if you want to create a hot runner mode configuration, then you need to go for this hot runner setting. Suppose you click on the hot runner, then it will ask you to select the what temperature you have to keep for the hot runner. You want to include the gates for the hot runner or not. Suppose you want to take the include the gate as well, then you can take forward with the hot runner mold and hot runner and gates itself, and select the wall gate. Means to say, I just show you, I selected this wall gate and click as a wall gate. So initially it is asking me to say initially it is open or closed. So I just select the open. So it will remain all the time open. If I select as closed, then it will all the time remain closed. Material will come from this location. It will not go through this gate because this is closed. It material comes only at this particular location. If I can add the controllers, and in the controllers I will able to edit or time delay pouring, means to say time delay injection I can apply to this particular gate. Suppose I want injection from this particular gate after the 10 seconds, then time I can put over here. So hot runner configuration you can do. After that there are some tooling configuration. Suppose you have to apply the vent just to escape the air. I just select this surface and select these edges as the vents. These are my vents. And mold, once you click on the mold, so automatically mold will create around your component. Then it will ask you to select the material and initial temperature. And coolers means the cooling channel. So I have already made the cooling channel, but if you don't have the cooling channel, then you can make just like this with the help of line. So I have already made, so I just directly assign. Once you assign, then it will ask you to select the cooling medium. The air is flowing through these pipes or some fluid is flowing through this pipe. Fluid means to say your water, some oil, anything. You can also put the temperature of that fluid. After that, insert means to say I have applied the insert just to make the hole properly. If I isolate this, then you can see it is a profile insert. Okay. After that, these are the processes. These processes are same as per some injection molding machines. For running the simulation, you just need to put the all input values required for running the filling, for running the packing simulation, for running the cooling simulation. And after that, if you want to put some machine parameter also, then you can also modify these machines value, your injection molding machines value. And last is to analyze the run. Once you go for the analyze, here you can also uh, set the what type of analysis you want to go for. You want to go for the fast analysis. In the fast analysis, you can also get only two type of analysis. First is the filling, second is the cooling. But if you go for the details, then you will able to get the results of the filling with fibers orientation. Fiber orientation will be available at what condition? If fiber is added to your material, input material, then only the fiber orientation will be given into the output results. Otherwise there would be no fiber orientation would be given in the output. So filling, packing, cooling, warpage, all the detail uh, means to say analysis you can do. Basically this final analysis, most of the people use the detail analysis to finalize the design. If they satisfy with their product design, if they satisfy with their die design, they in the last they just run a detail analysis to check all the things. So once you run the analysis and go for the results, then you can get the results in the filling stage. In the filling stage, temperature. In temperature, we can also check the behavior of my molten material in the cavity, how my how my molten metal is behaving in cavity. Okay, and next is the flow front. Mhm. Flow front temperature. Flow front temperature means to say if your flow front temperature is more than the temperature values, then you will able to burn marks on your aesthetic surface in the physical experiments. Velocity, how much velocity uh, has been applied by this molten material to get into the cavity. Pressure values, filling time, how much time is being taken to get completely filled, and air traps. So basically these are the reason for the air trapment. So this portion comes from the feeding system, but my finished part is this, the handles. So there would be no any kind of defects available in my component, but there are some you can see this some air entrapments you can see at the end. So just to eliminate this air entrapment, we need to do some more iteration and more exercise to exit this air from this location. In last, you can also see the weld lines. Weld lines means when your two front flows meet with each other at particular location at different temperature. So some weld line mark would be here and same just on the opposite side. And if I talk about the packing, in the packing stage, just a minute, just a so in the packing, you can check the temperature variation, how the temperature is changing, and these are the sink marks. Sink marks means those are some depression on your aesthetic surface due to the shrinkage. So these would be the sink mark region. These would be the sink mark region because there are more thick. You can see that there are more thicker region of the component. So that's why there is no uniform cooling is there. So if there is no uniform cooling, so component is not getting solidify uniformly. In the cooling stage, you can also check the uniformity of the cooling, how your component is cooling. Temperature variation. In the last is the warpage. Warpage means to say after the cooling, when your component is ejected from the die, and after the ejection there is some distortion happens to the component due to the non-uniform coolings. So here you can check the value of the distortion. So if I play the animation, then you will able to see the deflection is happening over here. Yes. So this is the warpage. So basically warpage is happening, but its value is very less, 8.8 into 10 raised to the power minus 4 mm. So very less, but distortion is there. If these type of distortions comes into the tolerance value, then we can consider the parts. If they cross the tolerance value, then we reject the parts. So this was from the injection molding product simulation. Product simulation, you can say, your product analysis, you can say, with the help of these analytical tool, you can freeze your designs and freeze your fabrications of the tools. So it was from my side about all these practical session that I was covered in my last session. Covered in last session just by the presentation only, but last session I did not give you glimpse of the tools, how the thing goes into the tools, and how we can proceed with the setups and run the analysis and post processing and visualize the results. So uh, this was from my side about the practical session. If you have any question and any doubts, then you are free to ask.
Participants are free to ask any question. If any part in the topic explained in the designing explained by Sharad sir is not clear, I guess there are no more questions, sir. Thank you so much, Sharad sir, for the wonderful explanation of the software and how its properties can be utilized in manufacturing the products.
Okay, thank you, thank you so much.
Thank you, sir. Thank you so much for the great knowledge. The feedback link will be shared shortly in the chat box only, and after filling the feedback, participants are free to leave for today. And tomorrow again in the morning, we'll all meet at 8:45 a.m. And tomorrow first session would be taken by Dr. Dinesh Khanduja. It is on the topic of role of manufacturing, role of organizational culture in manufacturing excellence. And he's professor in mechanical engineering department at NIT Kurukshetra. So dear participants, after the feedback, you all can leave for the day. Thank you.
Dear participants, wait for a minute. I am posting the feedback link. Wait for a minute. Please find the link in the chat box. After filling, you may leave now.